Hi, this is Mrs. LaBarbara. This is Physics Chapter 9, Current, Electricity, and Magnetism, Video 9. Today's topic is magnetism. The objectives are: know what a magnet is and its properties, know how to describe a magnetic field, know the magnetic properties of Earth, to understand how magnetic fields are generated, to understand how a compass needle is used to find a direction, to be able to select sketch diagrams of magnetic fields in areas near a single bar magnet, a single horseshoe magnet, and systems of bar magnets, to be able to select or sketch the direction of a compass needle when placed near a magnet. Magnetism. Here are the horseshoe magnet. As you can see, this is called a magnetic field. Here is a pencil is suspended. And here shows a magnet attracting needles. So magnetism refers to physical phenomena arising from the force between magnets, objects that produce fields that attract or repel other objects. So it's just a phenomenon of magnets. A magnet is any piece of material that has the property of attracting iron, such as the nails or steel. Magnetism may be naturally present in a material, or material may be artificially magnetized by various methods. So magnets may be permanent or temporary. So materials which can be magnetized are called ferromagnetic material. What is magnetic field and how it is created? So the cause of magnetism is from the property of atoms. So we have learned before atoms have a positively charged center called the nucleus, and is orbited by one or more negative charged particles called electrons. So the electron spins as they travel around the nucleus, which contains protons and neutrons, much like the Earth spins around the sun. As the electron spins or orbit the nucleus, they produce a magnetic field. As you can see, here electron spins as this travels around the nucleus. So this spinning of the electrons produces a magnetic field. As a matter of fact, not just electrons, any charged particles produce magnetic field. If a proton is moving, it produces a magnetic field, or alpha particle or any other charged particle. When they move, they produce a magnetic field. Not all atoms have a magnetic field, though. Even all the atoms have electrons. Why is that? All the electrons produce magnetic field as they spin and orbiting the nucleus. However, in some atoms, two electrons spinning and orbiting opposite direction, that pairs up and the net magnetic field of the atom is zero. As you can see, this green and the yellow may cancel out each other, right? So materials with one or more unpaired electrons are magnetic. Materials with small attraction to a magnet are called paramagnetic material, and those with strong attractions are called ferromagnetic material. Iron, cobalt, and nickel are examples of ferromagnetic material because they are very attracted to the magnets. So as you can see, if you have some left, not this up and down cancels, but some are left. Not all the fields are aligned, so when canceling spins are accounted for, the net magnetic field remains. So the material like this is magnetic. Magnetic domain. A magnetic domain is a region in which the magnetic fields of atoms are grouped together and aligned. Let's take a look. So here is an unmagnetized iron nail. So this area, all the atoms, their electrons spin in the same direction. And here is another one in the same direction. So each area is called a domain. So they are like miniature magnets within the material. However, as you can see, these two cancels. Up and down may cancel. These two cancels because they are in the opposite direction. So the one that's not cancels maybe have slight magnetic property. You can magnetize this nail. When you magnetize it, rub it with a magnet it will make all this domain align to each other. Therefore, this nail will become magnetic. It will attract, if you put another nail next to it, it will attract the other nail. Magnetic properties. So the property is attracting iron. So if you want to know if a material is magnetic, you can put it next to the two like iron nails. And if it attracts, it's magnetic. It also has two ends. Those ends called poles. It has two ends. So each magnet, doesn't matter how small it is, it always have two ends. North pole and south pole. North pole points to the north of the earth and south points to the south of the earth. No matter how many times a magnet is broken, each piece always have two poles. Like poles repel each other, unlike poles attract each other. It's kind of like positive and negative charges, but for charges, it can exist by itself, but not the poles. Poles does not exist by itself. Whenever you have a north pole, there is also a south pole. Compass. So compass, the needle of a compass is a small magnet. So the north pole of the compass actually is marked with N, usually have a red color. And where does this red pointing to? It points to the north direction, which is the magnetic south pole. So here's the Earth. North geographic pole, that's the north, is actually the south magnetic pole. So here is how the magnet in the field will pointing to. The red always pointing to the magnetic south, which is the direction of north. North magnetic pole is on this end, and that's a south pole, which is geographic, north. Magnetic fields. The region where magnetic force exists around a magnet is called a magnetic field. It's very similar to the charge. So the region around the charge is electric field. The region around the mass have a gravitational field. It's the same concept. So magnetic field allows magnets interact without touching. So magnetic force is another non-contact force, just like gravity and electric force. A magnetic field exerts a force on any moving charge and can be measured and detected by this effect. So here is a bar magnet. A bar magnet create a magnetic field around it. So if you put a needle here, it will be attracted either to the south or to the north. This is the picture, actually iron filings. You put iron filings around the bar magnet, you will see all these lines, because this is due to the magnetic field around the magnets. So magnetic field lines, rules for field lines directions. So a lot of times you are asked to draw the field lines. The direction is defined as the direction of north pole of the magnets would point in the field. So it's always from north to south. If you put a magnet, the compass here, the north will pointing this way, pointing to the south. So the direction always from north to the south. That's outside magnet. That's mostly what you have to draw, just outside. But you need to be aware inside is from south to north. So the lines is really kind of closed. It's a closed line, okay? Magnetic field lines never intersect. So the magnetic field is strongest where the lines are closest. Where the lines are closest, when it's near the magnets. So that's kind of like common sense. If you put a needle over here, it doesn't have enough field strength to be attracted to the bar. But if you put like a nail over here, it will most likely attract it, because over here the field is stronger because it's near the magnet. Now let's take a look at magnetic field maps. So if you have two bars, north and south, the field is always going from north to south. Looks like this, okay? It's coming into the south and going away from the north. So remember, this is not charges. So some people, it's very easy to make mistake. The magnetic field is north and south, not positive and negative. Here you have two bars that's north and north facing each other. So north is going away, they will repel each other. So these are the magnetic field lines and coming toward the south. Here's a horseshoe. Horseshoe is going always from north to south. Looks at the edge, it's not quite straight, it bends a little bit, but in the middle, it's a straight line. Let's take a look at this example. Determine the direction of the magnetic field lines at each point. Where is the field strongest? So at A, if you put a compass over here, it will pointing to the south. If you put a compass over here, the south will pointing toward to the north. So north would be pointing away. Over here, north would be pointing to the south. And over here, the north will be pointing to the south. So where is the field strongest? Where it's closest to the bar, which is point C. Another example, determine the direction of magnetic field lines at each point. Where is the field strongest? So let's see magnetic field lines. So over here is pointing away from north, right? Over here, the north always pointing to the south, north away from north. And over here, north away from north. Over here, north pointing to the south. So where is strongest? You see where is closest. I think field is strongest at F because that's where it's closest to the bar. Another example, determine the direction in which the compass will point. Compass, in this case, north always pointing to the south, north pointing to the south, north pointing to the south. So similarly, north pointing to the south. North is red. Okay, north pointing away from the south. Another example, the diagram below represents magnetic field near a point P. So here is P, okay? If a compass is placed at P in the same plane as the magnetic field, which arrow represents direction, the north end of the compass needle will point. So this direction is going that way. So this side would be north, this side would be south. So if I put a needle north, always pointing toward the south, so it would be answer B. That's it for today. Thanks for watching. See you next time.